So if you recall, just before the fire alarm went off last week, we were discussing, we were trying to go deeper into the definition of liquefaction. And we had started our discussion with this definition of liquefaction. So it is a sudden loss of shear strength of a granular soil mass, which is saturated, and it is often triggered by some kind of disturbance, some kind of vibrations, and usually when we talk about soil liquefaction, we say that those vibrations are happening because of an earthquake, although it can happen, a localized liquefaction can also happen if there is another source of vibration, for example, a blast load, a blast that you may cause to clear a pathway, to excavate a tunnel, for example. So we are looking at regional liquefaction, right? And then we had started our discussion with this Moore-Coulomb failure criterion, and we are saying that we are restricting our discussion to granular soils. So for granular soils, the shear strength tau is equal to sigma prime tan phi prime, right? And we say that liquefaction is the loss of shear strength. So loss of shear strength means the left hand side of this equation becomes 0, and that can become 0 only when something happens to the right hand side. And on the right hand side we have two components. The first one is effective vertical stress, and the second one is this shear strength parameter phi. Now if one of these two becomes 0, then you have lost shear strength. Okay. Now let us look at the first component, sigma prime, how it can become 0. It can become 0 when pore water pressure equates the total stress at any given point in time at a given depth, at a point of interest. So if that happens, then sigma prime becomes 0. And the second component is phi prime. So phi prime is coming from the grain to grain interaction. So if somehow this grain to grain interaction is lost, so for example the grains become suspended, they are no longer in contact with one another, then your phi prime will be lost, and again the knock-on effect will be that your tau will be to 0. Now we had a little discussion about what happens when you have this loose mass saturated with water, and when we have. So this was the discussion that we were having last week. So you have this saturated soil mass. It is loosely configured, but now all the void spaces are filled with water. Okay. Now you will have some hydrostatic pressure. So that is your hydrostatic pressure. And after that, what we said, okay, because of this presence of water, you have on each grain you have a force which is acting at the base of each grain, and which we call as the buoyant force, Fb. So the weight of the grain is acting downwards, and you have Fb acting upwards. So just because of the presence of water, all the soil grains have become lighter by an amount equivalent to Fb. Right now, let us, for example, take, in addition to this Fb, let us assume that we also have an upward flow of water. We will try to answer that. I think this was the exact point where we had to stop our discussion last week. But let us assume that we have this upward flow of water. Okay, so the grains have already become lighter by an amount equal to Fb, by an amount equal to the buoyant force. But now we have this upward flow of water. We will try to answer that in a moment. Why do we have this upward flow of water? But let us assume that there is upward flow of water. Now, because we have this upward flow of water, there will be an energy drop between the top face and the bottom face. And because of this, you will have an additional force acting at the base of each individual grain. And that we call as the seepage force. Okay. So we have W acting downwards. We already had Fb acting upwards, so the grain had already become lighter by an amount equal to Fb. But now we also have this Fs, the seepage force. Okay. Now, if the combined effect, the combined magnitude of Fs and Fb is such that it overcomes the weight of this grain, then the grain will be suspended. And imagine that this happens to all the grains in close vicinity to this grain. So this grain is suspended, this adjacent grain is also suspended, and you have all grains being suspended. So there will be no interaction between between individual grains. And if that happens, then your soil friction is 0, phi prime is 0, and the knock-on effect will be that your tau will be 0, the shear strength will be 0. Okay? Now we have to answer the key question. So this can happen when we have on each grain Fs and Fb. Fb will always be there if the grains are submerged in water. But how come we have this Fs? So that is what we need to answer. Okay, now let us assume that all these soil grains, so we had a big fish tank, for example, and we had put these spheres, which we are saying that these are representing soil grains. So these granular spheres, we have filled this fish tank, and then we have put some load at the top that we are calling as overburden, and also the void spaces are all filled with water. Now let us say that we take a wooden mallet and we hammer the outside of the fish tank. Okay, so with each hammer blow, you are creating some waves. Okay, so you are creating some disturbance. And because of the disturbance, these grains will try to roll and slide past one another. Okay? And by the way, why we are trying to hammer this? Because we are trying to say that this hammer is, we are trying to simulate the effect of earthquake. So where you have a loosely grained soil mass, saturated soil mass, and it is subjected to disturbances created by earthquake. So there are some vibrations. So those vibrations will result in will also be captured in these soil grains, and since this is loosely packed configuration, these grains will try to roll and slide past one another, and they will transition to a slightly tighter configuration because we have a lot of space. However, in doing so, what will happen is that you have pore water in the void spaces. So the pore water will get compressed. Okay? Once it gets compressed and it has nowhere to escape, the hydrostatic pressure suddenly rises to a new pressure. Okay? So in fact, let us look at the first one. We have this transition, a loosely packed configuration is being transitioned because of the effect of earthquake. And because of that, you have a tightly packed configuration. But during that very short duration of time where you have this earthquake, few seconds, the water is being compressed. It is so it is being compressed and it has nowhere to escape. So the pore water U will increase suddenly. Okay, and at the same time, since it is incompressible, so it will also try to exert equal and opposite reaction on these grains. So rather than they being coming together, there will be repulsive forces. Okay, so these repulsive forces will also result in these grains moving apart from one another rather than trying to come closer to one another. Okay, so we have pore water pressure increase suddenly, and we also have these repulsive forces which are trying to move these grains apart. Okay, so what happens here is you have hydrostatic pressure, it becomes very high, it takes a very high value, and of course because of these repulsive forces you have this loss of grain to grain contact. Now in addition to that, of course within this short period of time, this high pore water pressure will try to dissipate, and the easiest route with which it can dissipate is this water starts to come to the surface, right? So when it is starting to come to the surface, you notice that there will be an upward flow of water. So that upward flow of water will exert further force on each grain that we say is a seepage force. So seepage force is because of this upward flow of water, and upward flow of water is because the excess pore water pressure will try to stabilize, and it can stabilize only by following preferential paths, and the preferential paths are only possible when it tries to come to the ground surface. So you have an upward flow of water. We have answered that question, why there is an upward flow of water. So because of that we have Fs and Fc. In addition to that, you have this repulsive forces acting on these individual grains. So all of this is happening in a very short period of time. Over a period of time, this pore water pressure will dissipate gradually, okay, and this configuration will transition back to a tightly packed configuration. But before doing that, there will be a state where these grains will no longer be in contact with one another, and at that point defines the state of liquefaction. Okay, so you have these grains which are in suspension, and because there is no grain-to-grain contact, you have very high pore water pressure, and it will gradually dissipate. So at this stage, the soil has lost all its shear strength. There is no grain-to-grain contact. But after some time, it will transition back to to another equilibrium where you have a relatively denser configuration of individual grains, and the pore water pressure will dissipate. But liquefaction has already occurred. Now, during that time, when liquefaction was occurring, imagine that if you had a structure on top of it, so it will not be able to withstand the forces, it will just collapse. So after some time, it will transition back to hydrostatic pressure. Now also, in liquefaction, we also notice sand boils at the surface. Okay, so let me see if I have that first slide. From first lecture. Yeah. So you notice that we have, as an aftermath of liquefaction, we have this dome-shaped structures at the ground surface. We also notice a lot of granular soil at the surface, some water at the surface, and this central portion, central crater. Okay, adjacent to that, you have this soil which has come to the surface. So that typically happens as an aftermath in an aftermath of liquefaction. So this pore water pressure, which is very high, it will start to dissipate, but during the process of dissipation, there will be an upward flow of water, and this upward flow of water will happen by following. The water will tend to follow some preferential paths, and as I have explained, it can only come to the surface. During the process of this pore water pressure coming to the surface, it collects all the sand that comes in its way. Okay, because it is pressurized, so it digs some sand and it dumps at the surface. So these are those preferential paths, and after some time, there will be some settlement, because a loosely packed configuration has transitioned to denser configuration. So there will be some surface settlement, and this dome shape. So you will have the sand boil. So all the sand will be collected around this, and you will have central portion, which is that small crater, and you will see this type of shape at the ground surface. So if you happen to do a reconnaissance survey as an aftermath of an earthquake as geotechnical engineers or structural engineers, if you notice these type of things, then it is a very important precursor to liquefaction. You can clearly identify that liquefaction has taken place. You will have granular soil mass at the surface, you will have water, and you will have these typical crater type central dome type structures. So liquefaction happens in saturated sand and silt. So let us go back to the definition of liquefaction. Okay, and it happens when we have high void spaces, because it is those high void spaces which are initially filled with water, and during vibrations caused by earthquake, these void spaces allow the soil grains to move and roll and slide past one another. If we had a denser configuration, then the movement of grains will not be to the same level. So the degree of movement will not be to the same level. So it is also important that to have liquefaction, you need to have a relatively loose soil mass, so that you have the earthquake can allow the transition to take place, and in that you are letting the pore water to for water pressure to go very high. So this also gives us a very important clue how we can mitigate against liquefaction. So the most important thing is a loosely packed soil mass. If that is not the case, then we can perhaps avoid or reduce the chances or minimize the chances of liquefaction. So we can have a denser configuration now rather than allowing the earthquake to transition from a loose configuration to a denser configuration. So this way you can achieve, so if you densify the soil beforehand, and if you spot that from your soil investigations, you spot that yes, there is granular soil mass and it is in a loose state, you may go for some ground engineering measures to densify the soil so that that site can be safe against liquefaction. Now, why do you think clays cannot liquefy on its own? Sorry? Yes, okay, very good. So yes, if you recall the Moore Coulomb failure criterion, tau is equal to C prime plus sigma tan T prime. So cohesion will always be there, that is one thing. What about the shape of clay particles? So clays are usually platy particles, okay, but here what we are talking about is granular soil mass which eases these rolling and sliding phenomenon. Okay, so because of the nature of clay particles, because of the shape of these clay particles, it is very unlikely that clay will be liquefied on its own. So as per the definition, you need to have a granular soil mass, you need to have relatively loose soil mass, and also it needs to be saturated. So with this, if you look at these different profiles, which of these are quite likely to liquefy? Okay, so let us look at, so your friend says loose sand is very likely to liquefy. Very good, because you have loose sand here and it is, so of course it is loosely configured and you have water. So this is very likely to liquefy. And after that you have silty sand. So yes, you have slightly smaller particles, but it's still it is granular soil, and you have soil mass. You have this submergence. Okay, so this is also likely to liquefy. What about silt? On its own, this is also likely to liquefy, but the probability of this liquefying is not as high as this one, because you have very small particles now. Then you have clay. So you have clay, it is not likely to liquefy. There is no water. You have clay, but you have some water. It is not likely to liquefy. The difference between A and B is presence of water. Now coming to profile F, we have predominantly it is clay, but there is some evidence of sand as well. So on its own, it is unlikely to liquefy. Now on site, we do not normally see profiles like this. So you see you have 2 meters of soil, and if this is ground surface, we really have a layered soil profile, which may look something like this. Okay, so just before going to the next slide, so profile A, B, and F. So A, B, and F, they are highly unlikely. Profile C, D, and E. So C, D, and E, they are quite likely. And out of these, if we want to compare, then D is most susceptible to liquefaction because it is granular soil mass, bigger, and it is loose and saturated. So let us move to a layered soil profile. Okay, and if you are asked to identify the most susceptible layers with regards to liquefaction, what will be your answer? So do you all agree it will be loose sand? Okay, so it will be loose sand, right? So loose sand and silt to some degree are likely to liquefy. This is not going to liquefy, and plastic clay and clay, they are unlikely. but still you need a trigger to cause liquefaction. So for example, so what I mean by that is, if you artificially make this soil profile in a fish tank and you leave it there, nothing will happen. You need a trigger. You need earthquake vibrations. You need some source which causes disturbance. Okay? But you need to pass a certain threshold, because each soil will have a certain resistance against liquefaction. You need to pass a certain threshold which needs to be breached, and only then liquefaction will occur. So what we are looking at now is a method which we will learn to assess the liquefaction potential of a given site. So the first thing is that we need to have all the favorable conditions. It should be loose, relatively loose soil mass. It should be granular. It should be saturated. But still, there should be a threshold which needs to be reached in terms of the disturbances. So we will now see how to assess the potential of a given soil mass which might cause liquefaction. Yeah, so this is what I have written. So liquefaction likely soil layer will liquefy only when there is an earthquake of a certain magnitude which overcomes the soil's threshold, soil's resistance. So that takes us to an interesting subtopic within this part, and what we are going to look at is a method with which we can estimate the soil's potential, initiation of liquefaction. Now, all the theories that we normally see with regards to assessing the potential of liquefaction were originally proposed by Harry Bolton-Seed, and just like Carl Terzaghi is called as the father of soil mechanics, Harry Bolton-Seed is normally referred to as the father of geotechnical earthquake engineering. So he did pioneering work on liquefaction potential in 1960s and 70s, quite way back, but is still very, very powerful for us to understand. Of course, this theory has gone several modifications, as you can imagine. It is research, so it evolves, but the basic concepts more or less remain same. And the approach that he proposed is called as the cyclic stress approach. So we are going to learn the cyclic stress approach to assess the potential of a given site. Now, in cyclic stress approach, what we do is, so again, referring back to the example of fish tank. So you have a soil profile. You have artificially made it in lab. You have put everything in a fish tank, right? Now, there are two things which we need to look at. The first is, what is the soil's available resistance, and what is the load induced by earthquake. Both these quantities we need to assess, okay, and we need to assess them in similar terms. And where the soil's potential is less than the load induced by earthquake vibrations, we will say that liquefaction may happen. So we have to now calculate both the quantities. Now, typically in a cyclic stress approach, what we do is we plot the shear stress of the soil and also shear stress induced by earthquake forces versus depth. Okay, so we plot a profile like this. So this is for the earthquake, so equivalent cyclic stresses induced by the earthquake, the orange line, versus depth. And we also plot the soil's available resistance, okay, cyclic liquefaction resistance of soil, where the earthquake induced forces are higher than the soil's available resistance, and in that zone we will say that liquefaction is occurring, and we perhaps need to take some mitigating measures. I'll come to this when we do an example, what sort of mitigating measures we may take, and what is the advantage of actually constructing this type of profile, shear stress versus depth. Yes?
Green line is the shear stress.
So green line is the soil's available resistance, available resistance against liquefaction, and the orange line is the cyclic stresses induced by earthquake. So, for example, so in simple terms, this is the load, and this is the resistance. So orange line is the load, and the green line is the resistance. Now the key is how do we estimate these two quantities. So that is what we will do. But in general, this is what we are looking for. Now we have to estimate two quantities here. So the green line versus depth, and this orange line versus depth. If we know how to calculate these two quantities, our job is done. We can plot this type of profile and see where liquefaction is occurring. Okay. Now both the things, soils available resistance and earthquake induced forces, both the things in cyclic stress approach are calculated in terms of cyclic stresses so that we can compare similar things. Okay. So now the next steps are about understanding how to calculate values for this green line and values for this orange line. Now earthquake-induced loading, the first one. Okay. Now you know that when there is an earthquake, it will generate some shear stresses. Okay, and you will have shear stresses versus time plot, and it will be quite erratic. Okay, so with time, you will have this erratic shear stresses versus time plot from real earthquake time history. Okay. Now this obviously conveys us quite a few things, but still it is not very useful. So what people do is they take the peak of this and say that we transform this real earthquake time history into uniform time history, and they take a weighted value of 65% of tau max. So whatever tau max was there, say it was 30 kPa, it's 65%. Is the uniform cycle, and they say that this much of stresses are happening in a given equivalent number of cycles. So they transform the real earthquake time history into uniform time history. And obviously this will be dependent upon the magnitude of earthquake. Okay, so we already have a plot. So as your earthquake magnitude increases, your 0.65 tau max requirement will also increase. So you have these three graphs. So usually people go for the mean value. So whatever magnitude of earthquake is, you calculate the equivalent number of cycles that are required to cause 65% tau max. So this is how we will be calculating equivalent number of cycles. Now tau Tmax, which is the maximum shear stress, and tau cyclic, which is the equivalent cyclic. So tau cyclic is 65% of tau max. Okay, so this is also coming from experiments. Now, so 0.65, as I said, it is a weighted factor. Now tau max on ground can also be found by this. It is the ratio of A max by G, which is A max is the maximum ground acceleration, divided by acceleration due to gravity. So it does not have any units, A max by G. Sigma V naught is the total stress at given location times RD. RD is a stress reduction coefficient. Okay, now that is interesting. So stress reduction coefficient takes into account the amplification or de-amplification of seismic waves. What do I mean by that is that if you have an earthquake, say at a depth of 28 or 30 meters below ground surface, which will be quite unlikely, but let us say usually they are very, very deep. But let us say that you have say 70 meters, still it is a shallow earthquake, so 70 meters below the ground surface. Now from there you will have different waves which will propagate in different directions. Those waves will also come to the surface. Now as they come to the surface, their effect will get amplified because you have with regards to the 70 meters depth. As they propagate towards the ground surface, these waves are encountering relatively looser and looser soil. So its effect will get amplified. So its effect will be maximum at the ground surface, and it will be slightly reduced as we go deeper. So that stress reduction factor RD takes into account this amplification if we are considering with regards to to a certain depth, or deamplification as we are going deeper into the ground. Okay, so RD is obviously 1 at the ground surface, and it reduces as we go deeper into the ground. And obviously, as you can imagine, this also should vary with earthquake magnitude. So you have different earthquake magnitudes. So 5.5, 6.5, 7.5 on 8. And if you have any other earthquake, you can linearly interpolate or extrapolate if required. So it takes into account amplification and deamplification effects of earthquake. Now, how do we estimate the liquefaction potential of a given site? So it is very simple. The first thing is we calculate the, it can be done in 3 simple steps. The first one is we calculate the equivalent cyclic stress ratio induced by earthquake, okay? And that ratio is tau cyclic over effective vertical stress. Tau cyclic is 65% of tau max, or effective vertical stress at our point of interest, at location of interest. Okay, so that is step 1. This is the load, this is the orange line if you want to refer to that graph. Then in the second step, we want to calculate the soil's potential, soil's available resistance, but we want to calculate that in terms of cyclic stresses. Okay. Now for that, we take the help of a standard penetration test, SPT. Okay. So with SPT, okay, let me go to the next slide. I'll come to that in a minute. So what SPT means. I hope some of you may already know what SPT is, but let me quickly give you a recap of what an SPT is. So one of the methods of soil exploration is by digging up a borehole in the ground. Okay, so you go to the site, you excavate the soil, you create a hole in the ground. Okay, and then we can do 2 types of tests while creating a hole. We can do in situ tests while we are creating this bore in the ground, and also we can extract the soil samples, take it to a lab, and do laboratory tests on the extracted soil sample. So you have in situ tests and you have laboratory tests. Okay, now obviously there are certain advantages and disadvantages. We are not going into the detail of that, but very quick recap. So in situ tests could be good. The advantage of that is that you are not disturbing the soil. So whatever in situ test you are doing it on actual soil without disturbing its original state. So they are more reliable. They are relatively quick. You don't have to transport the soil sample to the lab. You prepare small samples, small specimens, and test them in the lab. And there are 3 very quick tests that people do on site. So SPT, CPT, and DCPT. So standard penetration test, cone penetration test, and dynamic cone penetration test. So what we are looking at is this SPT, which is an in situ test. Okay, I'll come to that in a moment now. On the other hand, laboratory tests, which are conducted on soils which are extracted from a borehole, they are obviously disturbed because you have created disturbance, although people try to be very careful by varying the sampler size and all those things, but still it is a disturbed state. But the advantage of a laboratory test is that you can do detailed investigation by performing a variety of tests. Of course, you will have some limitation here. You can do only very few tests, but here you have the luxury of doing a lot of tests. Now let us look at the SPT. Okay, so this is an in situ test, one of the in situ tests that people normally do. So what they have is a borehole, okay, and you have this sampler inside it, and you have the top of this sampler, which is called as an anvil, and then you have a hammer. Okay, so what they do is so this hammer can be moved up and down, and it has a known weight and it falls from a known height. So on the sampler you push the sampler into the ground and you give these blows on top of the head of the sampler. Okay, so in each blow you are giving the same potential energy because the mass is fixed. It falls from the same height, so NGH is same. So what people do, so it needs to be pushed, the sampler needs to be pushed to 450 millimeters into the ground. Okay, out of those 450, the number of blows that are required to push the last 300 millimeters is reported as SPT number, raw SPT. Now you can imagine very easily that if you have loose soil, then you would require less number of blows to push the sampler by 300 millimeters. If you have strong soil, if you have dense soil, then you would require large number of blows to push the sampler. So this gives us, so SPT number is going to give us some idea about the state of soil in that borehole. Okay, and they do these tests at different depths. Okay, so they do these n values at different depths. So at the end of it, what we will get is a depth versus n number profile. Okay. So this is what is written here. A borehole is made in the ground at a required depth, say 1.5 meters. So they create a borehole and then they do this process of pushing the sampler into the ground. They will push 450 millimeters, but they disregard the first 150 millimeters to allow for some unevenness. And then so a sampler is lowered into the ground and rested at the base, and then they push it. So the number of blows required to penetrate every 150 millimeters is recorded while driving the sampler. I will check this. I think it should be. I will double check this. Is it 150 or 300? I think the first 150 is disregarded.
50 centimeters.
Sorry?
15 centimeters by 1 dial.
Is it 15? Okay. So sorry about that. So then it is correct. Okay.
Total is 45.
Okay. Then what we will get? So the number of blows required for the last.
Last 30.
Oh yeah.
This is the first.
Yeah, okay, so it is correct. So first 150 is disregarded. The number of blows required to penetrate the last 300 millimeters is reported as that value. So that's what I said. Okay, yeah, thanks. So a weak ground will have a smaller end and vice versa. Okay, a larger end means high resistance to penetration of the soil sampler into the ground, and you need you need larger end value. Now this also tells us, this may also be very relevant when we are talking about liquefaction. So if you have loose soil which can be penetrated easily, then that is also likely to be liquefied easily. On the other hand, if you have denser soil, then it is likely to be difficult to liquefy. Okay? So if I go back to the profile, so this is how we will get this soil profile. So you have depth versus n value. Then these n values, so that is raw n value. Then you have to add, correct this n value by applying several corrections, rod length and all those things. I'm not going into the detail. And 60% efficiency, so it is called as N60. So raw n is converted to N60 by applying several corrections. And that N60 is further corrected to account for the overburden pressure, and that we call as N160. But N160, the raw value is coming from the original, and so the N160 is coming from the raw values of N. Okay, so if you have a smaller N, your N160 will be small. If you have a higher N, your N160 will be high. Now this is what is plotted in this graph. Okay, so with N160 on x-axis and cyclic stress ratio required to cause liquefaction on y-axis. So this is the soil's available resistance with greater N values captured in greater N160 values. The soil's resistance is high. Okay, So if you have N160 of 10, the soil resistance is only 0.15, for example. If you have N160 of 20, for example, then soil's resistance is 0.3. Okay? So this is the soil's. So the first step was to calculate CSREQ, that is the earthquake-induced loading. And the second step is to calculate the soil's resistance in terms of cyclic stresses, and that we readily get from this graph. Okay. Now this graph is plotted for 3 different fines. Okay, so we have 3 different fines. We have almost negligible fines content, we have 15% fines, and we have 35% fines. Just by looking at the graph, for the same n value, as your fines content increases, so let us say that your N160 is 20. For the given N160 of 20, as your fines content increases, you have a higher resistance that needs to be breached by earthquake forces to cause liquefaction. So why do you think it is like this?
The fines increase, the less amount of sand is there, the liquefaction chances increases.
Liquefaction chances reduce.
Yes, sir.
Yeah. Very good answer. Anybody else would like to help me with this answer? So my question is, with increasing fines content, why do I have a higher resistance provided by soil?
Because they're close together.
Sorry?
They stay close together.
Yes, so they are already closer to each other. Very good. So thank you very much, both of you. So let me go back to maybe this graph, this one, or maybe with water. Maybe this one. Okay. So if you have one type of soil, okay, here you have these grains, soil grains, and imagine that they are of same size. Okay, so you have uniform soil. Okay, then you have these void spaces. So all these void spaces are filled with water. In the second case, imagine that you have these grains, but in addition to that, you have some very small grains as well. So those grains will naturally occupy these void spaces. So when they are occupying these void spaces, in the event of an earthquake, you have relatively less chance for these soil grains to roll and slide past each other. And once you have restricted the ability of these grains to move, you have actually restricted the pore water pressure to increase to the same levels as before. So with increasing fines content, you will have less chances of liquefaction. Okay, so that is what is shown in that graph, that with increasing fines content, the soil has greater and greater resistance against liquefaction. So as N160 increases, the soil's available resistance against liquefaction increases, and percentage fines affects the soil's resistance, but you know how it affects. So it is always good if you have a well-graded soil, so you have gradation of different sizes rather than a uniform soil. So a uniform soil is likely to liquefy at relatively smaller earthquake-induced loads, while a well-graded soil, where you have proportion of different particle sizes, the chances of liquefaction are comparatively small. So a lower percentage of fines results in a smaller resistance against liquefaction, and more fines occupy the voided spaces between the soil grains, thereby allowing less space for coarser grains to move, and as a result you have less chances of earthquake. Now this graph, one more thing that to add about this graph is that this graph is plotted for an earthquake magnitude of 7.5. You know that earthquake magnitudes are not always going to be 7.5. So if that is the case, where earthquake is of 7 magnitude, 6.5, 6, or even higher than 7.58, so there has to be some correction factor that we need to apply to the value that we calculate from this. So there is a correction factor which is denoted with Km, and Km is 6.9 e to the power minus m by 4, where m is the magnitude of earthquake minus this. And since it is an empirical relationship, so there is a control on this, so it need not be more than 1.8. So it should always be less than or equal to 1.8. Now what will be the value of Km if m is 7.5? Will it be 1 or 0?
What is the factor? We multiply by 6.
Yes, so the correction factor will be 1 for m is equal to 7.5, and you can verify that with this equation. So you just need to put m is here 7.5 divided by 4 times e, and you will get Km is equal to 1. Okay, so for m is equal to 7.5, Km is 1, and the CSRL m for the given magnitude, the cyclic stress ratio required to cause liquefaction, so that is what is written in the bracket, the first bracket, CSRL m means for a given magnitude is equal to the value that you read from this graph, but the value is only for 7.5 magnitude, multiplied with Km if the magnitude is different than 7.5. So these are the two steps. Then the third step is you take the ratio of these two quantities, whatever you have calculated. So in general, factor of safety is resisting forces over driving forces. Here we have resisting stresses over driving stresses. Right? So the denominator is coming from earthquake, and the numerator is coming from the soil's available resistance. So wherever this quantity is less than this, your factor of safety against liquefaction will be less than 1. Okay, and that means liquefaction is likely. So if FSL is less than 1, liquefaction occurs. Now these steps are repeated for several depths to develop a liquefaction profile of a given site. So we do these calculations at various depths, and we calculate CSREQ, step 1. We calculate CSRL, step 2, and we compare the ratio of these two quantities for that depth to report FSL. We move to the next depth, again calculate those two quantities and do a comparison. We move further down and calculate these two quantities, do a comparison. So this is how we will be able to plot to come up with this profile. So this is the result of step 1, this is the result of step 2, and this is the comparison. The question says the figure below shows a typical irregular stress time history of an earthquake. The magnitude of earthquake is 7.5, and estimate the amplitude and number of loading cycles of an equivalent series of uniform stress cycles. So what we have here is basically time, tau, and it needs to be transformed to right? So we have a real earthquake stress time history, and which is irregular. And we have to estimate the amplitude and number of loading cycles of equivalent series. So by amplitude, what I mean? So this is the real earthquake, and this is the equivalent. So the amplitude of this is from here to here, and equivalent number of cycles is from here to here. So these are the two quantities that I have to find. Agree? So what is the amplitude? The first one, or tau equivalent, we call it as tau cyclic. .65 tau max, isn't it? And tau max is any one of these. So maximum value is approximately 30. So this is my tau max. This is my tau max. So you can find this value, isn't it? And then we have to find this in how many cycles this 0.65 tau max is happening. And for that, the magnitude of earthquake is given. So what I will do is, I'll go here and use this. So 7.5 magnitude earthquake is here, and the equivalent number of cycles will be here. So this is the first answer, 0.65 tau max, and this is approximately 15 over here. Next problem. Shall I go back to the previous problem? Is that, do I? Okay, no problem, thanks. So this is the answer of the previous problem.
Just can we have it in the same file under the problem directly?
Yeah.
So
Yeah, obviously. So you have it. So just to let you know, so far on Blackboard, I have uploaded the solution like this. So this is from our last week's example. So you have this on Blackboard. In addition, you have this lecture podcast. So whatever I'm writing is captured there. But this is also typed, so it is there. I think this was a feedback that I got from your class rep in the very first lecture, that you want my typed solutions, and that is what I have done on Blackboard. So you have all these typed solutions on Blackboard, and after today's lecture, I will be uploading this thing, whatever we are doing. That will go on Blackboard. Okay? No problem. So if I go back to the next example, which is here. So below is a profile of a site which is subjected to an earthquake shaking with peak ground acceleration of 0.15 g. So that means tau max is given. It is 0.15 g. Now it says estimate and plot the variation of maximum shear stress with depth, that is tau max, versus depth. And we also have to compute and plot the variation of equivalent uniform shear stress cycles with depth. So that means it is very simple. So from this one, maximum shear stress, and from equivalent uniform cycle, what we have to calculate is basically two quantities, tau max and tau cyclic, isn't it? These are the two quantities that we have to calculate. Now we have to calculate this at different depths. Okay, so we have to identify the depths at which we will be calculating these quantities. Now usually it is the top surface and the bottommost point of interest. So by that logic, it will be calculated at this depth, and at this depth plus it will also be calculated at depths where there is a change in soil profile, so that means here, and also a change in groundwater table condition, which is here. So I will have 4 different depths. Why I am doing this is because, if you recall, tau max is A max by G sigma V naught times RD. Now sigma V naught will be different at different depths. Okay, so that is why I will be calculating this sigma V naught at these 4 depths. So if you go to the next page, I think you have, so you have this table now. So in this table, I have now explained why I have z equal to 0 at the ground surface, why I have z is equal to 9 at the bottommost point of interest, and then 2 intermediate depths. One where there is a change in soil profile, here 3 meters, and the other one here at 4.5 meters. So for that table, I am measuring z from here. Okay. Now can you please try to populate this table?
All of the values are 1. RD will be 1 for all of them.
No, RD will change. Oops, sorry. So what will be sigma V naught at z is equal to 3 meters? So anybody with the answer here for z is equal to 3 meters?
49.5.
49.5, very good. So let me write this here. So this will be 16.5 times 3, and this is 49.5. What is sigma v naught at 4.5 meters? So I have calculated 49.5 up to this level. Now I have to calculate here. So that will be 49.5 plus 18 times 1.5. So if I and please make a note, this is total stress, okay? So what will be total stress at 9 meters? So we have calculated this as 76.5 up to here. Now I have to take into account the soil which is here, okay?
You need gamma saturated.
Yes, we need gamma saturated, but can we find gamma saturated?
Need E.
So you are given gamma buoyant, which is gamma sat minus gamma W.
So this is.
So gamma sat is gamma B plus gamma W, which is 11 plus 10, and this is 21 kilonewtons per cubic meter. So we know what is gamma sat. You multiply that with Z, which is 9 meters. Well, no, with 4.5.
So gamma B is gamma submerged.
Yes,
bulk.
yeah, buoyant. Yeah, I mean you can get that idea from the value as well. So value is very small. So this is, I normally write it like this, so that if I have made a mistake in the previous step, I can identify that thing. Otherwise, if for example you have made a mistake in this calculation, and if you do not write these calculations like this, and if you just write 49.5 plus this value, then your error will carry on, just in case if you have made this mistake. So I normally write it, write this thing in every step. It's entirely up to you, by the way. So okay, so let me put it back. So 16.5 times 3 plus 18 times 1.5 plus 21 times 4.5, and this is 171, right? You go back to the graph of RD for the given magnitude, and you calculate, where is RD? Yeah, this one. So with this you read the values of RD for the given earthquake magnitude, okay, and put those things in the table. There's hardly any difference for the first three values, so 0.98. Try to read it to the best, as best as you can, 0.96, and here you have 0.88. So tau max, we have everything. We have sigma V naught, we have RD, so we have this and this. A max by G is 0.15. So we have this thing as well. You just put it in this formula and find these values. You times it with 65% and you get tau cyclic. Okay? Okay, now the next example. So here, so it says, for the data given below, determine the extent to which liquefaction would be expected for an earthquake with m is equal to 7, with acceleration time history as shown below. Consider fines to be less than 5% and assume gamma 16.5 and gamma buoyant as 11. And it also says that the water table is at a depth of 3 meters. Okay? So let us try to draw a soil profile. So I have this soil profile maybe in a different color. So this is my ground surface, and this is my groundwater table, and groundwater table is at 3 meters. Now the first depth is 1 meter, the second is 2.5, the third is 4 meters. So the first depth is 1 meter, the second is 2.5, and the third is 4 meters, and so on. So these are Z. Okay, so what we have to do is we basically have to calculate where liquefaction is occurring for these depths, and to do that what we are actually looking at for is basically those 2 steps. So we will be calculating CSR EQ for every step, for every depth, and we will be calculating CSRL for every depth. We will be making this comparison and reporting that in terms of the factor of safety required to cause liquefaction. Okay. Now in this lecture we cannot do these calculations for all the depths. So what we are going to do is to take one sample depth and we do these calculations. Okay, so our sample depth is 8.5 meters. So we are doing these calculations only for this depth, so which is maybe this one. So this is 5.5 meters. So we are going to do these calculations for this depth. So you have to do, this is step 1, and some of the calculations I have already done here. You have to calculate a step 2 and you have to compare this. Okay, so can you please try to fill the gaps here? So there is something missing here, something missing here, something missing here, and few things here as well. So I think the first thing that you should be calculating is sigma V naught at the depth of interest. And in fact sigma V naught prime and sigma V naught. And once you do that, your calculations will become very easy. You just have to put this in these equations. Okay, so what is sigma V naught prime? Effective vertical stress at the location of interest, which is 8.5 meters. So anybody would like to give me the answer, please? Has anybody calculated this? Anyone from here? So you have to calculate sigma V naught prime and sigma V naught at this depth. Sorry? 154.5. My calculation is slightly different. Maybe I'll double check that. So let us first calculate the total stress. Total vertical stress. And this is, so for the dry soil, which is up to here, so this is 16.5 times 3. So 16.5 times 3 plus, again with the same logic as we had done for the previous example, the buoyant unit weight is given. So gamma stat will be 21. So plus 21 times 5.5, and this is 165. Right? Now effective vertical stress is sigma V naught minus U, pore water pressure, and this is 165 minus 10, which is gamma W times 5.5, and this is 110. Is that what you were saying? Oh, sorry, I misheard you. My apologies. Sorry. Okay, thank you. Okay, so we have got both the quantities. Now I can put these things in these equations, and .65. Well, I need to first find out what is tau max. 0.2.
A max by G is given. Yeah, so A max is this one. A max by G is directly given from here. So 0.2 times sigma V naught, 165. You calculate the RD from, I'm assuming it as 0.88 from the graph. And this comes out as 29.04 kilonewton per square meter. And I put it back in 29 in this equation, 0.04 divided by sigma V naught prime, which is this one. And this is 0.172. It won't have any units because in the numerator you have stresses in the denominator. So of course it is just a number. So that is the step 1. Now for step 2, you have to refer to the graph. Okay, so step 2, you have to refer to the graph. So whatever n value is given, you have to read it according to the percentage of fines given. Okay, so that will be your CSRL. But this graph is only for 7.5 magnitude, so our magnitude is 7. So we will apply a correction factor. So from that graph, our CSRL is 0.11. Okay, and since it is not same magnitude of 7.5, so we will apply a correction factor, and for that the correction factor calculations are so 6.9 e to the power minus 7 by 4 minus 0.058, and this has to be less than or equal to 1.8, and this comes out as 1.141, and this is true, so we will accept this value, put it back here, and that is what I have done here. I get this CSRL as 0.125. And in the third step, I just take the ratio of whatever I have calculated in step 2 and step 1. Clearly, this is less than 1, so it is quite likely to liquefy. Make sense? Okay. Any questions on this? Okay, so this way what you can do is you can actually tabulate all the results. Okay, so whatever we have done so far, you can tabulate them. So we have calculated these things for depth of 8.5 meters, where n value was given as 10.9, and we have got a factor of safety of 0.73, which is less than 1. Okay. Now here we will see a direct correlation of n value and the factor of safety value. So if you have a smaller n value, okay, so for example here, your factor of safety will be even smaller than what we have calculated. And vice versa, if your n value is big, so for example here, then your factor of safety is high, naturally. Okay, because n value, if you recall, tells you how loose or relatively dense a given soil is. Okay, so you have a higher resistance against liquefaction for relatively higher N values, and vice versa, you have relatively smaller resistance for the same earthquake when you have smaller N values.
So there's some soil good for construction, but more risky at the same time.
No, so what I'm saying is, so I mean, the first thing is that we normally develop a profile like this, Z versus this factor of safety. Then we try to assess what it physically means. The first thing it is telling us is that there is a direct correlation between N value and the factor of safety that we obtain. And that makes sense because the soil's resistance is dependent on the N value that we have chosen. So smaller N value will give me lesser resistance against liquefaction. A higher N value will give me high resistance against liquefaction. And remember, all these calculations are done for the same earthquake. Okay, so the only change is as we change the depth is these N values. Okay, so the same earthquake is able to cause liquefaction here, but it is not able to cause liquefaction here. Right? Now, what does it mean actually? How do we take this into account? So think about different structures that you may construct, okay, and think about the type of foundations that you may have. So, for example, if you are constructing, if you say that you have performed this analysis for a site for where you are going to have a new construction, okay, and this is a liquefaction soil profile, say up to 20 meters depth, and from structural loads, you say that a shallow foundation is good enough there. Then a shallow foundation is usually placed at, of course, shallow depths, which are likely to liquefy. Okay, so perhaps you may need to go for some ground engineering measures to avoid liquefaction at this site. Likewise, if your structural calculations say that yes, shallow foundation is not good enough, but you want to still provide a foundation, you are going deeper into the ground, then perhaps say from your calculations your pile is going to be 7 to 8.5 meters. Then again at this depth liquefaction is likely to happen. Okay, so perhaps you may need to avoid this depth and go further deeper into the ground. So this also dictates the depth of pile foundation that you may have. Okay, then one interesting thing that we get from here is, so that is the relevance of this with regards to the type of foundation that you are going to construct of developing this profile. Then one interesting thing over here is something like this. Sorry, not this one. So if you look at these, if you look at these three depths, okay, so this depth 11.5 meters is unlikely to liquefy because the factor of safety is more than 1. Then the depth of 14.5 meters, so 11.5 is unlikely, 14.5 is unlikely, but you have a very weak layer sandwiched between these two. So it is quite likely that this will liquefy this layer and this layer as well, because this is a very weak layer, so it may liquefy this layer. Now think about the fact that you are trying to place a pile foundation, and you are saying that yes, pile foundation is likely to be 11 meters deep, but that will be a bit risky because from here you have this layer likely to liquefy, although it is not directly liquefying, but indirect liquefaction of this layer. So again, that is something that you may need to be mindful of, that you may have a very, very weak soil layer sandwiched between comparatively stronger layers. So stronger layers may not liquefy on their own, but you may have some effect of liquefaction on them because of comparatively weaker layer. So in summary, you can have something like this. So FSL, which is this last column, has a direct correlation on the n value. Higher the n value, greater is the factor of safety, and vice versa. Layers sandwiched between two layers, liquefiable layers, may liquefy, and we need to think about this with respect to a foundation that we may construct for a given site. Any questions? Yes, please.
So for soil profile like that, what would be the solution? Because then we have so many different variations, it's very large.
So it depends on what type of. So for example, if you have a very good question indeed. So if you're trying to say that you have a shallow foundation, shallow foundations typically have depths of about 2 meters, right? And you see that yes, it is likely to liquefy. So you may need to do some ground engineering measures. So try to compact the soil by doing vibrocompaction and things like that. So you need to make it stronger artificially. So again, if you look at the definition of liquefaction, so perhaps it means that the soil is loose, so densify it beforehand rather than wait for the earthquake to densify it and risk liquefaction at this site. So you may need to have some you may need to take some ground engineering measures for that. If you are going deeper into the ground, then perhaps a simple option could be that you ignore this depth, for example, so there is no skin friction for this depth. Sorry? So you may ignore the skin friction, skin resistance of the pile coming from this depth because this is highly liquefiable, and as a result of that, to balance the same load, you may need to go deeper. You may need to have longer piles, for example. So you may need to use. So these are the consequences of this type of profile. Either go for ground engineering measures, try to strengthen the soil, but we cannot strengthen the soil at deeper strata, which will be cost prohibitive and impractical. So we take an alternative approach of going further deep into the ground. Okay. Any other questions? Any questions? Okay, so moving on. So dynamic soil properties. Okay, so now the soil properties, as you know, even under static conditions, are a bit complex to determine. Okay, because they depend on several factors. Especially when we are talking about granular material, we have been discussing about liquefaction. So let us start our discussion with granular material. So if we are looking at granular material, then depending upon the state of soil, your stress strain behavior might be very different. So for example, if you do a direct shear test on a dense soil, okay, then that soil might dilate. So something called as the dilatancy behavior of a dense soil, where with increasing shear stress, with increasing axial strain, your soil, instead of getting compressed, it starts to dilate, it expands. Okay. Sorry. An increase in volume. Okay. So your volume might increase. If you do the same test, if you repeat the same test on a loose sample, then obviously the soil will compress, so there will be a reduction in volume. So volume will decrease, while depending upon your relative density of the soil. Okay. Now usually the rate of loading is immaterial for static soil, for static tests, okay? Because for the type of structures that we normally deal with, the rate of loading, how fast and by how much we apply the load on a given soil mass, it is not very significant, as the shearing behavior of soil usually remains uninfluenced by it. But on the other hand, when we have the case of dynamic loading as induced by an earthquake, we are looking at large strain behavior, okay? Because earthquake is going to cause large strains. So for static cases, the rate of loading and the amount of strain that we generate in a soil is not very significant, at least in comparison to the dynamic state, because for dynamic state it causes large deformations as in earthquakes, and as a consequence of that, whatever soil properties we determine need to be replicative of actual soil behavior. And on site, because of earthquake forces, you have large strains happening on site. So whatever soil properties we determine should be determined by considering a significant strain value. In other words, our dynamic soil properties are going to be strain dependent. Otherwise, whatever we determine is not applicable on real sites. Okay. Now we have two types of, so within strain dependence, we have two types of, or two classes of tests: a relatively low strain method and a large strain method. Okay, so we do these dynamic soil property tests by having two different methods, a low strain method and a large strain method. Now within these two categories, we can obviously either do in situ tests, on field tests, or we can do laboratory tests. Extract the soil sample, take it to a lab, and do these large strain or low strain tests in a lab. Okay? Now there are several soil properties that are of interest to us. Now so for example, density, Poisson's ratio, damping, and stiffness. When we talk about the dynamic soil behavior, then out of these four, the first two are the most important. So that is the stiffness and damping of a given soil mass. Okay? The other two quantities are not that significant, at least in comparison to stiffness and damping, and also they usually vary in a very small range. So they have variation in a narrow range. So we can live with that. Now critical in the problems that we normally tackle with in geotechnical earthquake engineering, as I said, stiffness and damping are very important, both at low strain and high strain values. Okay. Others do not seem to have a significant consequences on the properties that they obtain, and perhaps they also, and the reason is they also vary in a narrow range. Now, what is the advantage of field tests, and especially the in situ tests? So we are again we have touched upon this briefly in this SPT. So allow the soil to be tested in its original state. We are not creating a lot of disturbance, and hence we are able to capture the existing side effects on whatever values we obtain in situ. Those side effects could be because of existing state of stresses, they could be because of chemical, thermal, and structural conditions of a given soil mass. And obviously we do not need a soil sample. We test it on site in large areas and measure the response of large volumes of soils, so which is not possible to do in laboratory. We have to mimic soil conditions, we have to mimic field conditions in laboratory on small samples. But on the other hand, for field tests, we have that advantage of testing relatively large volumes of soils. And this is also important that these tests, to mimic the actual site conditions, they need to be performed by replicating the same amount of deformations, the same amount of strains that are likely to happen on site. Field tests, however, they do not allow us to understand the effect of existing in situ conditions. We cannot vary those in situ conditions unlike what we can do in laboratory. We can vary inside the test conditions, and pore water drainage cannot be significantly controlled. So that poses a challenge. Not all tests can be performed when we have pore water there. Now, whatever we field test we do, we then make use of some standard empirical correlations to deduce other properties. We will see that later on, what type of properties we calculate and what type of empirical correlations we can use to calculate other soil properties. So this is a rather indirect way of measuring dynamic soil properties. So for example, if we are interested in calculating shear modulus, dynamic shear modulus of a soil, we estimate it by calculating or by measuring the shear wave velocity, and we back calculate it. We back calculate the value of shear modulus. So these give us some indirect measurements rather than direct measurements of actual soil of the exact property that we are after. Okay, so we have in situ tests. Now, in situ tests are further subcategorized into two types of tests. One is surface test, the other is a borehole test. Okay. In surface test, obviously, whatever test we are doing at the ground surface, and by doing something, we are extracting valuable information. I'll cover that in a minute. What is that something? In a borehole test, obviously, we create a borehole in the ground and do some testing within the borehole to extract valuable information. So tests performed on the ground surface. For the surface test, usually these are less expensive. Okay, they are relatively quick to perform, and these are preferred in soils where you cannot drill, you cannot do a borehole test. Okay, so in addition to these advantages, this is perhaps the option when you cannot go for a borehole test. On the other hand, borehole usually provides some valuable information about, so it provides information from borehole excavation about the soil type, so you can visually see that. Soil characteristics, groundwater table location is also a very important thing that we get by looking at the information that is extracted from a borehole test. And since the results that we get from these borehole tests, because you are drilling deeper into the ground, so they are perhaps comparatively more representative of the actual soil profile that you are likely to encounter. And hence, the interpretation of results is you have a better confidence on them rather than in comparison to the surface tests. As I have said, you have two categories of tests, so depending upon the level of strain that we can go for. So you have a low strain test. It operates at shear strains which are very, very small. So gamma is the shear strain, which is less than 0.001%. So we need to ensure, in low strain tests, we need to ensure that the gamma is not high so that it does not induce the nonlinear stress-strain behavior of soil. So we are still operating in linear regime with regards to the stress-strain behavior of soil. And it usually involves, so low strain tests usually involve measurement of body wave velocities, from which we calculate the shear moduli. Now, since this is a low strain, so since this category of tests is a low strain category of tests, so whatever modulus we determine is categorized as low strain modulus. So this is something that is important to keep in mind. We will come to that in a minute later. What do we mean by low strain modulus and how strain value influences the shear modulus that you take into account. Then the surface tests, or the low strain tests, you have some very common geophysical tests. So most common type of low strain tests are within this category of seismic geophysical test. It involves two things. The first one is a source where you create body waves. From where you create body waves. Okay? So you create a source from which you can create body waves, and then you try to capture how these body waves are behaving inside a soil medium. Okay? And then you interpret. Sorry, I should have left this. Different ways in which you can create body waves. So you can put you can put an explosive at shallow depth beneath the surface of the earth, and from that explosion some body waves will generate, and you try to understand the behavior, how these body waves are propagating through the soil mass. Then you can also create a vertical impact on the ground. So with this impact you are creating body waves, and sometimes you can also create horizontal impact in the ground, and again trying to understand the behavior of body waves. So you require two things: a source with which you can create body waves, and another station where you can record the behavior of these body waves. So let us look at the first one, the second one. So vertical impact cases where you are giving a blow to the ground. So a source is going to produce a pulse of different waves. So you will have surface waves, you will have shear waves, and you will have primary waves. Okay. Now their arrival times are measured at distant receivers. So you have this source, you have a receiver at this place, and you record the arrival time. So you also know how far you have placed the receiver. Okay, so you know the distance, and then you record the time that it takes a body wave to reach that receiver. So in other words, you can calculate the velocity of the body waves which are captured on a receiver, because you know the distance, you know the time. Distance upon time is going to give me the velocity. Okay, now P waves, so out of those different waves that are generated, P waves are going to be are the fastest. Primary waves are going to be fastest. So they are going to be captured. So the first wave that will reach a receiver will be the P wave. Okay, so P waves are the fastest, and their arrival is detected at different receivers placed at varying distances. Now, presence of groundwater is essential in interpreting the results. Now, primary waves can travel very fast through water, right? So if they are traveling faster, then obviously their velocity is being influenced by the presence of water. Okay, so there is obviously a danger of overestimation of wave velocity just because of the presence of water. Okay, and as a result of that, if we are using P waves to back calculate the soil's stiffness, then we have a danger of overestimating the stiffness, because P waves, whatever velocity we have recorded, if they have traveled through water, then that is not the actual velocity with which your P waves will be traveling. So there is a danger of overestimating this thing, and as a result of this, we normally go for S waves. So we use S waves, the shear waves, because shear waves cannot travel through water. So they are going to give us information about just the soil skeleton rather than soil skeleton and water as we may get for the P waves. We are interested in calculating the shear modulus of soil skeleton rather than shear modulus of the entire soil plus water mass. Okay, so that's why S waves is better. Now let us look at how it looks like. So we have this source. Let us call this as S. We have placed a receiver at a distance R. Okay. At this source, we are creating disturbance. So there will be a waveform which will be generated. Okay. So an impulse is produced at this source. So then we will have the P waves are the fastest to reach. They are the fastest. So this distance is known. Okay, so this is x. If we record the first wave that is received over here, we can calculate the velocity of this wave, and that velocity will be the velocity of P waves, because P waves are the fastest to reach. Now its arrival time is measured at the receiver R. We know what is the distance. So distance over time can give me the velocity of P waves. Now some waves will follow the direct path, S to R. Some waves will go down and then reflect back, depending on whether you have a change in soil profile. Okay, so some waves will obviously propagate through, some waves will reflect back. So the first one is your P wave. Now let us see how do we calculate. So for the direct wave, so from here to here, I know what is this distance, x, and I know what is this time taken, how much time it has taken to reach this receiver. So I can back calculate what is my P wave velocity. I know what is x, I know what the left hand side of this, TD. So I know what is my velocity, primary wave velocity. Now by measuring TD and x, the P wave velocity of the soil layer can be determined. Now for the reflected wave, so that was for the direct wave. Now for the reflected wave, you can do this slight mathematical jugglery here, that I, which is this 2I here, so half of this is I. So this you will have a right angle triangle. In that right angle triangle, x by 2 will be half of this divided by h, where h is the thickness of the first soil layer. So that will be your tan I. Tangent of I will be x over 2. So x over 2x. Now from this, if you put it, so then you calculate this thing so you measure the left hand side of this TR. We have already calculated VP in the previous step. You back calculate, and the only unknown will be your H. So with this we can calculate the thickness of this soil layer number 1. VP is from the previous step for direct wave. I know what is TR. I know how far I have put this receiver from source. So the only unknown is H here. So I can calculate what is the thickness of this first soil layer. So although we are doing a surface test, but it is giving us some valuable information about the thickness of the first soil layer. You also have a slightly different way of doing these type of tests, where you have a combination of source and receiver, and that you do by using this method called seismic cross-hole test. In this, what we do is we create 2 boreholes in the ground, and in those 2 boreholes, so I know what is the distance between these 2 boreholes, and in these 2 boreholes I lower a source in one borehole and I lower a receiver in another borehole. So these are small geophones. Okay, so I have this source over here, I have this receiver over here, and they are lowered at for the same depth, say 2.5 meters here and 2.5 meters here. And again I will do, so use 2 or more boreholes. So let us say that we have 2, one with the source, the other with the receiver, and the source and receiver are fixed at the same depth. Now I'll do the same thing. In this one I'll create some impulse. Those impulse will form some waveforms, and those waveforms will travel over here. Okay, so the wave propagation velocity of the material between these 2 boreholes is measured, and then what we do, we change the depth of the source and receiver. So we can move up or we can go down. So with that we get difference in velocities. So with this we can also develop a layered soil profile, because velocities are going to change when they encounter different soil medium. So obtaining measurements at several depths, either go down or up, I can develop a nice soil profile. You can do the same thing in one borehole. So you place the source at the top and receiver at the bottom, or you place the receiver at the top and source at the bottom of one borehole. Okay. So it is performed. So seismic downhole test is performed in one borehole. The principle remains same. So you create a disturbance of waveform in source, you capture it on the receiver. And with that, what you can do is you can obtain this type of soil profile, where we are measuring VP and VS. Okay, and as we perform that for different depths, so this depth is increasing. You have time, we get different type of soil profile. So you have fill, mud, clay, sand, and rock. So as the soil gets denser and denser, your velocity increases. And that is what is happening over here. So the other type of test, so those are the field tests that you can perform. The other type of test is a cyclic triaxial test. So I'm sure you must have heard about a triaxial test. Now in this one, the only change is in the first word. So I've added the word cyclic. So obviously this is a high strain test. So remember, we are trying to calculate dynamic soil properties corresponding to the anticipated level of strains on site. So this test in particular is a high strain test where large deformations take place. So in this one, the only change with traditional static triaxial test is that the axial load that we apply on top is cyclic. It cycles at a certain frequency, usually at a frequency of 1 Hertz. So the way we perform this test in static conditions is you have this soil sample, you surround this with confining pressure that we call as sigma 3, radial pressure, okay, all around it, and then you apply the axial load. You keep on increasing the axial load for a given confining pressure until the sample shears, until the sample fades, and then you plot the stress strain distribution for that given for a given value of confining pressure. You change the confining pressure, you repeat the test, and you repeat it again. Okay, this way you calculate the soil parameters for a static case. In this dynamic cyclic triaxial test, we do the same thing. The only change is in this axial load, it cycles at a given frequency, and then you again bring the soil sample to failure. One important thing that we get, because this is cyclic in nature, so one important thing that we get out of this is a hysteresis loop, hysteresis curve. A hysteresis curve will look like this, and it gives us two very important parameters. So on x-axis I have axial strain, on y-axis I have this stresses. So the size of the curve will give me damping, give information about damping, and the slope of the tangents. So the slope of this will give me information about the shear modulus, or how stiff my soil sample is. Now so coming to the soil stiffness, I can have two values of soil stiffnesses from here. One is tangential. So at any point I can draw a tangent to this, and the slope of that will give me the tangential stiffness, G tan, or if I join the ends of this hysteresis curve, then I will get a secant modulus, G sec. Okay? So it changes along the curve. Tangential stiffness, as you can imagine, is going to change along the curve, but G sec is not going to change, because for a given curve it is fixed. It is the slope of the line that you obtain by joining these secants. So it is this end to this end, and it remains constant. So it is not dependent on the level of strain. Now this is quite useful, but it is the G-sec is dependent on the level of strain for which we have performed this test. So if you increase or decrease the axial strain, then the slope of this G sec is going to change. Okay, so from that what we get is a backbone curve. So joining the tips of series of stress strain curves, that is G sec values for different strain levels. So my hysteresis loop is going to change its slope, and as a result of that your G sec is going to change, and if you join the peaks of these, you get a curve like this, which we call as the backbone curve. So now from this backbone curve, so you have this backbone curve, so the initial slope will give me the initial slope, which corresponds to very, very low levels of a strain, will give me the maximum shear modulus, which we call as G max, which we denote with the G max. And any other modulus for a given strain will be my G sec, G secant. So the slope of tangents drawn to the backbone curve will change, obviously, and it is going to decrease with increasing shear strain. So as we are progressing from this point to this point, the shear strain is increasing, but your G value is reducing. Do you agree with that? As we are moving from this origin to this point, as your shear strain is increasing, our shear modulus of soil is progressively decreasing. Now the maximum value of this is when we have very, very low strain, when we have the strain very, very small, so that it is this tangent, the initial tangent. Okay, so this has a very important, so we can only use G max by using this backbone curve only when we are confident that the soil is going to have very, very small strains on site. If we are expecting large strains, then we will be under designing our structure by considering G max, because that is not actual shear modulus on site when we have higher strains. This is only applicable when we have very small strains, G max. So the slope at the origin is designated as G max, and G max is applicable only to small strain values. So G max is normally obtained at shear strains which are less than this number, 10 to the power minus 6, very, very small strains. And one of the ways in which G max can be calculated on site is by doing a surface test or another geophysical test, which can give me shear wave velocity. And G max is the square root of the ratio of G max. I'm sorry. So G max is rho, which is density of soil, times shear wave velocity. So you can calculate this shear wave velocity by doing any of the surface tests on site. You multiply that with the soil's density, and you directly get G max. But this G max will be only possible. We should only use this when we are confident that our values of expected strains on site are going to be very, very small. If that is not the case, then we have to go for relatively smaller values of G. So this is the modulus reduction curve. So what, for very small strains, I can have the G equal to G max, but as you anticipate larger strains, then our G value reduces. Now coming back to the cyclic triaxial test, this gives us two different samples. This shows the results of cyclic triaxial test on two soil samples. One is for a loose sand, the other is for a dense sand. And for each case, I have three sets of graphs. The first one is tau cyclic versus time. The second is shear strain versus time. And the third one is RU, pore water pressure ratio. A value of pore water pressure ratio is nothing but the ratio of delta U over sigma. So how much pore water is increasing and that is normalized with respect to the effective vertical stress at a given point of interest. Now, if this ratio is equal to 1, then that means pore water pressure is equal to the effective vertical stress, and in that case, liquefaction is likely to happen. On the other hand, for a dense, so now these three graphs are also plotted for a dense soil sample. So you have this dense soil sample, and we notice quite a few things. The most important thing is that for loose soil, you require a small number of cycles to achieve liquefaction. So RU equal to 1 signifies liquefaction, and this is achieved at very small number of cycles. On the other hand, if you have a dense soil sample, then you require relatively large number of cycles to liquefy the same soil sample. And the other thing that you notice over here is the amplitude of tau cyclic. So here I have maximum amplitude of 20 kPa. For a dense sample, even though I have tripled this, so from 20 it goes as high as 60 kPa, and it's still, since it is dense sample, it is taking longer to liquefy. So this also tells us some very valuable information about what might happen and what actually happens on site. So we had a discussion that if you have a loose sample, then it is highly susceptible to liquefaction. If you have a denser sample, then it is less susceptible to liquefaction. And that is precisely what is shown over here, that for a loose sample, you require only a small number of cycles to reach full liquefaction. For a dense sample, you require very high, you can cope with even high number of repeated loading on a given soil sample to achieve liquefaction. And that is also, it can absorb 60 kPa for this sample, and it is only 20 kPa. So even though we have tripled the amplitude, it is taking longer for the soil sample to liquefy, just because it was originally dense and this was originally loose. Now we can also plot this thing in a slightly different way, and that we call as the cyclic strength curve. It provides a relationship between the number of cycles. So x-axis is the number of cycles, shear stress amplitude. So shear stress amplitude is y-axis, and density. So density is captured, so the initial void ratio. So density is captured in these four graphs. So what is happening as we are moving from top graph to the bottom graph in this? Void ratio is increasing. So void ratio increases means what happens? Is the sample becoming loose or dense?
Loose.
Do you all agree that as we move from top to bottom in this set of graphs, the void ratio is increasing, and increasing void ratio means you have loose sample. You have progressively loose sample as we are moving from top to here. And what should happen when you are having loose sample, relatively loose sample? It should liquefy at relatively smaller number of cycles. Okay? So we can also plot this type of graph, again coming from a cyclic triaxial test. So this is often normalized. So this cyclic triaxial test is often normalized with respect to the cyclic stress ratio, CSR, that we have seen previously. Now, if we do a simple shear test, which is slightly different than a cyclic triaxial test, then we can have cyclic stress ratio from a simple shear stress, simple shear test is the ratio of tau cyclic, whatever we get, divided by sigma V naught prime. So because it is normalized with respect to effective overburden pressure for that depth. And this is also, this tau cyclic over sigma V naught prime is also equal to CSR EQ that we have seen in step 1 of our liquefaction potential. Right? Now if you do a triaxial test, then CSR triaxial, so TX is for triaxial, it is the ratio of sigma DC which is this deviatory stress or failure stress, over twice of the confining pressure. Now with this we can also correlate that we can also find a correlation between CSR SS and CSR TX, and we can apply a correction factor. So this is an empirical relationship where people have applied a correction factor to the cyclic stress ratio that you achieve by doing a simple shear test and the cyclic stress ratio that you achieve by doing a triaxial test. Now CR is a correction factor in these equations, and that is already given by some researchers, and we can directly use these numbers to calculate CSRSS. Now laboratory tests, so that is how we can actually correlate laboratory tests to find out CSR EQ. But there is a small problem. The small problem is that whatever laboratory tests we are doing, this type of triaxial test, it is capturing information in a unidirectional stresses regime. Okay, so you are only able to compress the soil. Okay, so you have unidirectional shear stresses, but in an earthquake, your stresses are going to be multidirectional. So there is some disparity between what is happening on site and what we are trying to replicate in our lab by doing this cyclic triaxial test. Now Seed, again, the person who has proposed this cyclic stress approach, has suggested that the CSR required to produce initial liquefaction, that is CSR EQ, is about 10% less than that is required in unidirectional tests. So this gives us a good information, and we can live with that. So CSR EQ in field is equal to 0.9 times CSR triaxial. So we can do triaxial test in lab. You multiply that with this correction factor, and to take into account the unidirectional, this disparity, that in the test you are only operating in unidirectional stress regime, while on site, because of earthquake, you will have multidirectional stress regime. You factor it with 0.9 because it is said that the CSR required to produce initial liquefaction is about 10% less than required in unidirectional stress regime. So you factor this with 0.9. I think this will be a bit more clear in my view when we do an example, and that is what we will do now. So let us do an example. Now it says for a 5 meter thick sandy layer, groundwater table is found to be located at a depth of 3 meters below ground surface. We are given data from a triaxial test, which is shown below in this figure here. We need to estimate the maximum cyclic shear stress required to initiate liquefaction in sand for a magnitude 7 earthquake. We are also given soil parameters. So we have on x-axis number of cycles, on y-axis we have the cyclic deviatory stress, which is the failure stress, and we have performed this for a confining pressure of 150 kPa. So how do you think we should approach this problem? So these are the solution steps which will help us. So our end goal is to find tau max. Okay, that will be required to initiate liquefaction in a magnitude 7 earthquake. So how will we do problem step number 1? I think it is partially done in your handout. Well, not handout, so the soft copy of that. So maybe you can have a look at that. Any idea about the first step? So we have to find n that corresponds to 0.65 tau max. So what we have to do essentially is to go back here and use this graph. So for magnitude 7, what is 0.65 tau max? So what are the equivalent number of cycles in which the sample is likely to liquefy? Okay, so that is approximately, so for magnitude 7 we normally use the mean value graph, and that is approximately 9. Okay, so if I go back here and so this will be 9 from n versus 0.65 tau max.
The graph was with M.
Sorry?
The graph was with M. Or with
Yeah, I'm sorry. So it should be M. So yeah, it should be M.
So this is the value of 0.65 tau.
This is
the
the
value of N.
The value of n that is required to achieve 65% of tau max.
Cycles.
Okay. Now, what will be your step 2? So this is done. Step 2, find CSR TX. So what we will do is, we have found the n. So for that n, I will be reading the value of sigma dc, which is approximately 80. Why I will be reading this is because CSR TX is sigma dc over twice of sigma 3 prime. I already have sigma 3 prime. I'll be reading that value that corresponds to n equal to 9. Okay, and that will give me, so here I will write for 9 cycles. 9 is from here. Sigma dc is 80 kPa. Okay, so if I put it back over here, this is 80 divided by twice into 150. So 150 is this one, and this is 0.267. Now K naught is 1 minus sin phi. Why I'm looking for K naught? It is because I have to use a correction factor. So I have to use CR, and CR can be found by using this correction factor, and correction factor has a component of K naught. So K naught is, I'll be finding that K naught, and this is 1 minus sine of phi is 30 degree, and this is 0.5. Now for correction factor, there are 3 given in your notes, so you can choose any one of these 3. So you are given 3 theories. I can choose any one of these 3. They give slightly different answers, but since it is empirical, we can live with the difference that we have. So I will choose 1 plus K naught divided by 2, and this is 0.75. Now CSR EQ, you know, it is 0.9 CR, then CSR from the triaxial test. And this is 0.9 times 0.75 times 0.267, 0.18. Our ultimate aim is to find this, and to find this I need to know what is tau cyclic. To find tau cyclic I need to know what is CSREQ, and that is what I have found over here. Okay. I also need to know what is sigma V naught prime. Right? Now if I go back over here, it says a 5 meter thick sand layer. The groundwater table is found to be located at 3 meters below ground surface. So if I draw this soil profile, it is always helpful to draw a soil profile like this because it tells me what type of soil conditions I am operating in. Now this is a 5 meter thick layer. Okay, and the groundwater table is located at 3 meters. Right? Now, where should I calculate sigma V naught prime?
Depth of change, the first and the last.
We are looking at liquefaction, so it has to be somewhere here. Okay. Now this is 2 meters thick. So it depends. It really depends upon you. If you calculate it at mid depth of this, that will be good enough. So 1 meter depth for the soil layer which is submerged. Okay. So you can do these small calculations, and based on that, sigma V naught prime. I can calculate sigma V naught prime over here. So sigma V naught prime is 19 times 3 plus
11.
yeah 11 times 1, and this is 57, 58, 68. That goes over here. So CSREQ is 0.18. Times 68, and this gives me some number. You put this number over here and you will get the tau max from laboratory triaxial test as well. Yeah.
Can I just ask why it's not 11 multiplied by 2 when we have the layer of 5 meters?
Yeah, so you can do that at different depths. So as a sample, what I have done over here is I've calculated this at mid thickness of the liquefaction susceptible layer. You can do it for the next 1 meter as well. It's entirely up to you. But just as a sample, you can do this calculation at the mid height of the liquefaction susceptible layer. Sorry?
Thank you.
No problem. Any other question?
In case if you want to make it conservative, can't we take value which gives less effective stress? The depth which gives less.
Yeah, so for this case, we have 2 meters. Now it could be 7 meters as well. So in that case, you have to calculate. You have to do these calculations at several depths, and from that take the conservative value. Where the conservative value will be?
Yeah, but we haven't determined the point of interest until the last step on the.
Yeah.
So in this step, when I am considering the gamma dash, the sigma prime, seam bank want to be more decrease or more decreasing. So this will decrease the tau cyclic, and this will decrease the tau max.
Yeah. So you can take the conservative value, which gives you maximum tau max.
So I can take it at the depth of 3 meters per meter at the top of the water surface, or there is no chance of liquefaction.
I think that will not be very useful in my view, because it is not going to. I mean, you may have some indirect liquefaction, but usually you should consider for a layer where you have some submergence of soil, so it is submerged. Otherwise, we are not satisfying the first condition of liquefaction, that it needs to be submerged.
So even if it is 7 meters, 6 meters, I can take 1 meter to be conservative.
You can take it as well. Usually, it needs to be performed at the mid thickness of that liquefaction susceptible soil layer.
So even if it is big, I have to go more deeper.
So if this was 7 meters, then perhaps 3.5 meters will be good for this. Okay. Okay. Any other questions? Okay. So thank you very much.